Hello viewers. In this presentation, we shall see the important features and the internal architecture of Intel's 16-bit microprocessor, the 8086. We shall also discuss the concept of physical address generation in this microprocessor. The basic architecture of Intel 8086 is as shown in the figure. We shall discuss it in detail as we proceed along. Let us first of all see the advantages which 8086 has over the 8-bit 8085. The first advantage of 8086 is that of parallel processing. In 8085, the processes of fetch and execution do not proceed simultaneously. The opcode is first fetched from the memory by the memory read operation. Then this opcode is decoded and executed. During execution, the memory system is idle and there is no fetch operation. 8086, on the other hand, makes use of this idle memory time by prefetching the next instruction while executing the current one. This concurrent operation of fetch and execute accelerates the overall execution of the program and was made possible by dividing the internal architecture of 8086 into two separate units, the bus interface unit and the execution unit. The bus interface unit has the main function of fetching the instructions from the memory, while the execution unit simultaneously decodes and executes those instructions, thereby providing parallel processing. The second advantage of 8086 over 8085 is the capability of addressing 1 megabyte of memory as compared to 64 kilobytes in 8085. This is possible as 8086 has a 20-bit address as compared to a 16-bit address in 8085. The third advantage is that 8086 has a larger number of internal registers, thereby allowing software to be written more efficiently. Also, these internal registers can be accessed much faster, that is, 200 nanoseconds in 8086 as compared to 800 nanoseconds in 8085. The fourth advantage of 8086 is that it has the facility of hardware multiplication and division, which 8085 lacked. Finally, 8086 has better memory management and addressing capabilities than 8085. Let me now show you the 8086 microprocessor chip. 8086 is packaged in a 40-pin dual inline package containing approximately 29,000 transistors, which are powered by a single 5-volt supply. It has got 20 address pins, 16 of which are also used as data pins. Let us now discuss the details of the internal architecture of 8086. As mentioned earlier, internally the 8086 is divided into two main parts, the bus interface unit and the execution unit. The bus interface unit provides all the external bus control functions, including instruction fetching and queuing. The execution unit decodes and executes the instructions. Both these parts work simultaneously, thereby providing parallel processing. Let us see the details of the execution unit first. Its various constituents are 8 16-bit general registers, an arithmetic and logic unit ALU, the flag register, I/O control system and decoder unit, and temporary registers. AX, BX, CX, and DX constitute the general purpose registers in 8086. AX can be used as a 16-bit register and is called as the accumulator. It can also be used as two 8-bit registers, the lower byte AL and the higher byte AH. In addition to serving as general purpose registers, BX, CX, and DX also have certain special roles to play. BX is called the base register. This is the only GPR whose contents can be used for addressing 8086 memory. In fact, 8086 BH and BL registers are equivalent to 8085 H and L respectively. CX is called the counter register, as some instructions like shift, rotate, and loop use the contents of CX as a counter. Data register DX has a special function in relation to certain IO operations and in multiplication and division operations. The two pointer registers used in 8086 are the stack pointer SP and the base pointer BP. These are used to access data in the stack. The destination index register DI and the source index register SI are used for indexing, another new concept introduced in 8086. The 16-bit arithmetic and logic unit, ALU, has the same role which it had in 8085, that is, of carrying out the various arithmetic and logic operations. The flag register in 8086 consists of 9 flags. These flags are further subdivided into 2 groups, 6 conditional flags and 3 control flags. The flag register is shown in the graphics. Out of the 6 1-bit conditional flags, the first 5 have the same function and bit position as in 8085. These flags are CF, carry flag, PF, parity flag, SF, sign flag, AC, auxiliary carry flag, and Z, zero flag. The 6th flag is a new one introduced in 8086 called the overflow flag. This flag is set if an overflow occurs, that is, a result is out of range. It is meaningful for signed operations only. Additionally, there are 3 control flags which can be set or reset by the programmer. These were not there in 8085 and are: number 1, DF, direction flag. This flag controls the selection of forward or reverse processing in string operations. Number 2, IF, interrupt flag. IF is equal to 1 enables external maskable interrupts, while IF is equal to 0 disables these. Number 3, TF, trap flag. TF equal to 1 places 8086 in single step mode and is useful in debugging. Having seen the details of the execution unit, let us now proceed to the other part of the architecture, that is, the bus interface unit. The main constituents of the BIU are the 4 segment registers CS, DS, SS, and ES, the instruction pointer register IP, the internal communication registers, a dedicated adder, bus control logic, and a 6-byte instruction queue. The 1 megabyte memory in 8086 is organized as segments of up to 64 kilobytes each. There are 4 types of segments. The code segment is the section of memory that holds the code. The 16-bit CS register defines the starting address of this section of the memory. The data segment is a section of the memory that contains most data used by a program. The DS register points to the current data segment. The stack segment defines the area of memory used by the stack, with the SS register pointing to the current stack segment. The extra segment is an additional data segment and is addressed by the ES register. 8086 can directly access 4 segments of up to 64 kilobytes each, that is, 256 kilobytes within 1 megabyte at a particular time. The 16-bit instruction pointer IP is used to address the next instruction to be executed by the microprocessor. Since the address bus in 8086 is of 20 bits, the dedicated adder is used to generate the 20-bit memory address. The bus control logic is used to generate the various bus control signals like memory read and write and I/O read and write. The instruction queue stores 6 bytes of instruction code prefetched from the memory ahead of execution. These instruction codes are further transferred from the queue via the queue bus to the decoder in the execution unit for further decoding and execution. The internal communication registers and the temporary registers are used to store the various intermediate results during the calculations in 8086. Having seen the details of the internal architecture of 8086, let us now proceed to the physical address generation scheme used by this microprocessor. The 20-bit address of the actual memory location is called the physical address. Since registers are all 16-bit, so to generate the 20-bit physical address, we use a segment register along with another 16-bit register. The address contained in the segment register is called segment address, while the address contained in the registers BX, IP, SP, BP, SI, or DI is called the offset or effective address. In order to generate the 20-bit physical address, the contents of the segment register are multiplied by 10H, that is 16 decimal. This is implemented by appending 4 zeros to the right of the number in the segment register. Then the offset is added to the contents of the segment register so as to generate the 20-bit physical address. Let us consider an example of physical address generation in 8086. Let us consider the segment address to be in the code segment register CS with the contents 1000H. Further, let the offset be in the instruction pointer IP having a value 0111H. The first step in physical address generation is to multiply the contents of the segment register by 10H. This gives us CS equal to 10000H. Now we add the contents of IP, that is the offset, to this value of CS so as to get the required physical address. Thus, the 20-bit physical address is given by 10111H. In this way, we generate the 20-bit physical address from the 16-bit segment address and the 16-bit offset. Thus, CS gives us the start of the current code segment with IP giving the offset or the distance from this starting address to the next instruction byte to be fetched. Offsets have to be added to the other segments also to generate the corresponding physical addresses. The details of the offset addresses are as shown in the graphic. For CS, the offset is in IP. For SS, it is in SP or BP. Similarly, for DS, offset is in BX, SI, DI, or can be a 16-bit number. For ES, the offset is in DI. The segments can be continuous, partially overlapped, fully overlapped, or disjoint. Thus, the advantages of using segment registers can be summarized as shown in the graphic. If a program fills only part of a segment, another code, data, or stack segment could overlap the program's segment, thereby utilizing the memory more efficiently. Thus, the advantages of using segment registers can be summarized as facilitates the use of separate memory areas for a program, its data, and stack. Useful for multi-programming. A minimum of 4 different programs can be time shared, and better memory utilization. In this program, you have been introduced to 8086 and have seen its important features which have made it such a powerful and popular microprocessor. We have also discussed its internal architecture and the physical address generation scheme used. In the program to follow, you will be exposed to the pin details and memory organization of 8086. Thank you.